Right? Next Tuesday, am I right?
A week from today, yep.
Yeah, okay. So, did I give you the phase 4 or not yet? So I'm going to give you the phase 4 and post it this Thursday, you know. So as soon as you finish that one, I was going to give it, I'm not sure, I'm thinking about it, you know, to give you another simulation homework like the one Arno is working with you guys, but, sorry? Uh, uh, I'm not sure. Maybe you're gonna have one more homework number 4, and you're gonna have the project. Maybe not. Maybe I don't give you the third. You know, the third one I was thinking to give you the first 2 homework you did. You know, the second one especially the bulk. I was going to. This is one of the products we are working on. They call it charger, battery charger. You have a solar panels, and you have a battery. You want to charge your battery. They call them charger. You know, they call it solar charger. You know, battery charger. So basically, I was thinking to give you that one so you can do the maximum power point tracking on the solar panel and charge the battery. This is one of the projects right now. We're working for a company. It's called Outback in Seattle. You know, we're working on that one. I thought you don't have to build it, just simulate it. You know what I'm saying? I was thinking to give you that one. It's a very simple thing. You know, just the MPPT and already have the bulk converter design. But I may skip it. You know, I don't know. Maybe I'm thinking maybe I'll push you a little bit too much. You know, and if toward the end of the quarter, I know you guys are behind everything. And,
True story.
I don't know. I'm gonna think about that. And most probably not. We are gonna stop with the simulation homework there, and you are gonna have the phase 4 and the rest. On the final exam, you are going to take it in there, whatever is the time. It's Thursday, the final week, right? Because there's few people they have problems with taking the exam in the last day of the class. But no, we're not going to do it. So we'll leave it for the final week, final week. You know, the Thursday, I don't know whenever it is. But the presentation is going to be Saturday before the final week. You know, we start around 11 o'clock till we'll go maybe until 2 o'clock. I don't know, based on how much time you need, and we schedule that one. One person, I don't know, somebody, maybe not just one, maybe there are more. If you have any conflict that Saturday, you should talk to Arnold to schedule your time. Either before, for example, I think one of the students has an exam on Saturday. He mentioned in his email. So you are open from 11 to 2 o'clock, to present your presentation. You know what I'm saying? So if your exam is morning, the schedule for later afternoon. If your exam is afternoon, the schedule for the early, like 11 o'clock, something like that. But all the presentation should happen Saturday before the final week, okay? Before the exam week, let's call it, before the exam week. That Saturday, we should finish everything, okay? Now, going back to what we taught. I sent you already homework number 3. Homework number 3, 2 of them, they're simple. You can see they're like a steady state equation, and after that you go build a small signal model and you calculate the transfer function I'm asking you. You go through that you do it for Bach boost. I did it for Bach and boost here. You guys, you are going to do it for Bach boost, You do that one. Very possible you are going to have one question similar to that somehow in the final exam, just to let you know. I need to find a simple circuit, something like that, to give it to you guys. 2 of the questions, they are like that. One question is a design question. We are going to go through the design question today. We are going to solve one example. I'm going to go through the steps of the design, and this is when you did the second simulation homework, right, with the Bach boost, right? You did that one, right, already or not? So you look at that circuit you have, the op-amp circuitry you have. So you need to design those parameters, right? If you're a design engineer right now, you did it, I think, by trial and error. You change the value to get it fixed and working. But you need to design those values. You can use the same method we are teaching today, So last class we talked about the compensator type 2, and I think this is very incomplete. Yeah. Right? Yeah, because I shouldn't leave it here. Can I see where I finished last time? Somebody has a good note, so I can read it. Yeah. Yeah. Okay. So we went through the. We introduced the type 2 compensator. Now we know the plant equation, right? The transfer function of the plant is clear. If it is balk or boost or balk boost, you are going to do it in your homework, right? The plant is clear. The PWM generator transfer function is clear, right? The compensator, we said we are going to go through type 2, but there are many, many types of them. There is a PI controller, there is a P controller, there is a PD controller, D is a differentiator. PID, type 2, type 3, there are many, many types of these controllers. Now we are going to focus only on one in this course, but if you are interested, you can type it, in the compensator designed for DC to DC converter. I'm going to bring all these controllers for you. You can read them and work on them. We will work on only type 2 compensator. We introduced the circuit, what circuit it is. We calculated transfer function for that circuit, and we end up to come to this equation, I think. This one was a type 2. Or controller, I don't know, whatever we call it, controller or compensator. We had this circuit here. And we did calculate the transfer function for this system. The final answer was yeah. Right there. And we just simplify this one, we call this one S plus. This is omega Z, this is omega P. I think almost we got to this one, R to C. And there's another S here. This is after the simplification and kind of approximation of that one. And the last thing we said, the body plot for this one is going to be like this. Or let's call this one, this is a compensator. Let's call it TC, T compensator. This is a TC, and this is the phase of TC, or PTC. Let's make it easy, PTC, right? And the phase was like this. And we call this one boost, right? And what is this at this point? Is a PTC, right? This is a phase, and we call this one boost, right? Here. Now let's continue from here. And the full system is like this. We have a VREF, right? We have a VO, TC, I think we call it TM, T modulator, right? T what? TP, plan, right? VO, and we have a unity feedback, right? TOL, or they call it loop gain, or loop, this is a gain. What is the gain of this loop? Is this one times this one times this one times this one, right? But we define the TOL, open loop we call it. It's going to be TC, TN, TP. So, and if you remember, these are all 20 logarithms. Just I'm reminding this one. How much is the TOL? It's going to be TC plus TM plus TP, right? Right? Because you say 20 logarithm of this one is going to be 20 logarithm of this one, right? This is a times. Logarithm of A times B is logarithm of A plus logarithm of B, right? These are 20 logarithms, right? And phi-OL is going to be phi-TC plus phi-TM plus phi-TP. How much is the phi-TM? 0. It was 1 over VP, right? This one was a constant number, 1 over VP. The phi is 0. Basically, phi-OL is the phi-TC plus phi-TP. Keep this one in mind. And this is the compensator, and this one is the plan. Now, this is the only compensator, right? What we want to do here overall, the TOL. The TOL, we want to have something like this. Just I'm going to plot the TOL somehow here. It's going to be something like this. Something like this. Let me cross it here. This is a TOL, see? This is a TC. The reason I'm saying, look at here, the TOL, overall system, right? This one is going to be omega cross for this TOL. It's going to happen between, this one was omega Z, and this one was omega P, right? Omega Z and omega P, right? Somewhere, when we design this thing, the TOL is going to have a transfer function like this. Look at here. We said we want to have a high gain at low frequency. Look at the TOL. It has a high gain at low frequency, right? We want to have a low gain at high frequency. We are going to get rid of all those high frequency properties, either noise or whatever it is. And here is the crossover frequency, right? Here we are going to define the phase margin of the phi TOL, right? How much do you want to have a TOL? Right? Phi TOL. How much do you want the phase margin here to have? 45 to 60, number between those ones, right? Now, keep these things in mind. See, you can see somewhere here, I need to know how much is the gain of this TC, right? I'm going to call it midpoint gain. Let's calculate the midpoint gain. Let's see what I can call it midpoint. So I want to make sure I'm using the same name. Yeah. Compensator. This is for the compensator. I'm calculating this one. What was the transfer function of the compensator? I'm going to write it again here. TC was equal to, I said omega plus omega Z, right? Over S times omega plus omega P, right? What did I have here? A over A something, minus A or A? I'm not sure.
Minus A over S.
Yeah, minus A, I put the S here, minus A over S. Look at guys here, having S at the 0. Maybe you think why we select this one. Having S at a pole near the 0 it's going to increase the gain, right? If we didn't have this one, it will be flat here, right? Having this S by itself is something like this, right? It's going to give you very high gain here, right? That's the reason we want to have this S here. Just I'm going to tell you a little bit about this one. And after that, we need to go with the phase margin. I have to kind of flat out this one. So I use this one. And again, after that, I need to get a very low gain. You know what I'm saying? I'm going with another pole here, right? That's the reason we selected this way. And this circuit has this kind of transfer function, right? Now, we know omega p is very, very bigger than the omega c, right? We know this one already. And here, for calculating the midpoint frequency, means omega is somewhere between omega z and omega p, right? How much is the gain? If I want to calculate the gain at the midpoint, how much is it? I can go from here, right? The gain, I'll just replace let's write it here. How much is the gain? So TCJ omega, right? Calculating it. TCJ omega is going to be now taking this something here. We have a R2 C1. R2 C1. In the simplification we did.
So TC should be S plus omega Z.
No, I'm looking for this one to say. Let me write this equation one more time before we simplify it. We had this one, right? This is what we had. We had the TCS is equal to, I think, correct me if I'm wrong, it's going to be R2 C1S, right, plus 1 over S times R1, R2, C1, C2S plus R1 times C1 plus C2, right? I think we had this one, right? And we had one assumption, C1 was very, very bigger than C2, right? Because that one, I think we have one small thing wrong over there. So what we did, we said TC is equal to, and there was a minus somewhere here, right? There was a minus here. It's going to be minus 1. I'm factoring R2C1. Or I want to get rid of this one. Yes, I can write this one like this. R2C1 1 plus S plus 1 over R2 C1, right? Now, right? Yes, R2 C1. Now, if I divide this one and this one by R2 C1, we're going to get S plus 1 over R2 C1. This one is going to S times R2 C1 is going to go away, R1 C2 S plus R1 C1 plus C2, right? Divided by what? R2 C1, right? if C1 is much bigger than this one, yes, look at it. This is the where we made a little bit mistake, If C1 is very bigger than C2, this one is how much?
Approximately equal to C1.
This is approximately C1, right? This term is almost C1, right? Let's cancel this one with this C1, right? So we are gonna have R1 over R2, right? This here is gonna be S times R1 C2 S plus R1 over R2, right? Let's factor in this part, R1 C2, R1 C2. So this one is gonna be, we have a minus here, I have to do a minus again. I'm gonna factor this part, R1 C2 times, denominator is gonna be the same, here's a minus, I put it here, to C1 divided by S times S plus, if I factor R, it's gonna be 1 over R2 C. This is a transfer function. So here, I don't, when I did simplify, I have over there, in your note, correct this one. I don't know what mistake did I do, I didn't get this one. It's going to be negative 1 over R1 C2. R1 C2. Clear here? See, looks like we did something, I calculated this one in the last class. This term is different from what it should be. It should be this one, just correct out in your notes, Now, I'm gonna go back here. I want to calculate the midpoint gain. I want to calculate the midpoint gain. Midpoint means somewhere between omega z and omega p here, right? So TCJ omega is going to be equal to, let's come here. We have this one, right? Let's replace this one. Minus 1 over R1 C2 times, that one is then, I'm going to write it J omega plus omega z, right? Divided by J omega times J omega plus omega, right? The only thing that here, what we calculated before, just correct this one to R1 C2. Now I'm calculating the TC J omega, just I'm replacing S with the J omega, and this is the omega Z, and this is the omega P, right? We have omega Z and omega P. Now, let's calculate how much is the TCJ omega. It's going to be 1 over R1 C2, right, times is it correct? I calculated the amplitude of this one, the magnitude of this one, and how much is the magnitude of J omega? Is omega, right? This one is going to be this to the power of 2 and this to the power of 2, right? Now, we're going to assume something. We're going to have some simplification. If omega is very, very bigger than omega z and very, very less than omega p, right? Just is somewhere between, right? Just for simplifying this one. So if this one is very, very bigger than this one, a square root of omega 2 plus omega z, how much is it?
Omega.
Is omega. How about this one? This one is going to be omega p, right? The bigger one. Now let's use this tree. How much is the TC J omega? It's going to be 1 over R1 C2 times, so this one is omega divided by omega times omega p, right? Get rid of this 2, right? So it's going to be How much is the omega p? How much was omega p? This is omega p, right? 1 over R2C2. R1C2 times R2C2, C2 is going to cancel C2, right? So TCJ omega will be R2 over R1, right? That's a midpoint gain for the TC, right? It's going to be this much, which we want to happen at this point. We're going to do a little bit more calculation. The omega is here. Look at here. Now I know how much is my midpoint gain. I want to calculate the boost. And think about it. This omega is going to be omega cross 4TOL, right? Because we said we want to cross 0 here, where is the, we're going to have the phase margin, right? Now, let's calculate the boost first. How much is the boost? First of all, let's say, what's the, sorry?
You can calculate the phase margin and subtract from
Right. And, no, but I want to do something else. Let's say, phi TC. How much is the phi TC? Look at this. We have a S is a j omega, right? It's going to be minus 90 for this one, right? It's going to be minus 90 for this one. How much is here?
omega z over omega.
Plus arc tangent of omega z over omega, right? Omega z over omega, right? This is a j, yes. Plus arc tan omega z omega over omega plus minus because this one is in the denominator, right? This one is here minus arc tan of omega over omega p over omega, right? So I know this value, right? If I replace this one with the omega cross, I'm going to calculate this, right? But also I know, this is another thing, phi TC plus boost, how much is it? Is 90 degrees, right? Or let's think about it. This is a negative, right? Just I want to make sure. Let's give it a number. Let's say this is a minus 30, right? Just I want to make sure, because you can see here it's going to be negative, right? Minus 30. This is a minus 90. How much is the boost? 60, right? Let's see if that doesn't work. If you put here minus 30, because phi TC is minus 30, right? Plus boost is going to be, no, something is wrong. What is wrong?
Should be minus.
No.
TC plus boost is negative 90, right?
Boost is a positive 60. Right? Boost is a positive 60. So basically should be, yes. Right? No, plus boost. Am I right?
No. Phi TC minus
Yes.
Is it correct?
9.
I think it's right, right? Boost is going to be 90 plus phi TC, right? Because phi TC is negative, right? Plus 90 is going to be 60 here, right? Keep this one also here in mind. Now, we calculated the midpoint gain, we calculated the phi TC at any frequency we want, especially we can go through here. Now let's go through this steps. Minus 9 is the derivation. Okay. Now we are going to, yes.
What is the meaning of boost? If we
Boost
calculate
is going from this much is boosting up. It's bringing up the phase. It was minus
So
90.
it's always going to be phase margin.
Basically, boost is going to be where the CTC is the maximum, right? If you are going to calculate the CTC, if you are going to calculate the real boost, how much is the real boost? You should take a derivative of this one respect to omega, right? And equate to 0, calculate the omega, replace it here. It's going to give you the PTC and you can calculate the boost. Let me see, there's something here not doesn't make sense. Let me see. Yeah. Oh, you know what? You know what here? This one is opposite. Why? Let's look at it here. We have this one S plus omega z, right? And S plus omega p, right? You know what I'm saying? We made a small mistake here.
Should be omega.
Because when you if you calculate the TCJ omega, what the word there? Yeah, order is correct. Order is correct. That's it. So this one is going to be minus a over j omega plus omega z, j omega plus omega p, right? So this j omega is going to be how much? Minus 90. How about this one? It's going to be arctan of omega over omega z, right? I put omega z over omega. This one should be like this. And this one should be like this. Okay? And this is the omega, which is the, for the TOL is going to be omega cross. Now, let's start the process of how we're going to calculate this. I want to find the relation between the phase margin and boost also. I'm going to summarize all this stuff. Right now it's a little bit confusing, but after I calculate everything, I'm going to put them into order how we are going to go. I want to see what's the relation between the boost and the phase margin. Those are what I want to see on what's it. So we said phi TOL at omega cross. Right? See, this is omega cross. Right here. This is omega cross. I should draw this one again here, and you guys can see it. Let me put it again here. We have a TC was like this. Right? We have a TOL. I'm going to put it this way. TOL is going to be something like this. Let me do this. This is the TOL. And this is a phi TC. Just correct that one. You can see those things better. Now, phi TOL at the omega cross at this point is going to be what? Phi TC at omega cross, right? Plus phi TP, right? and this one is how much? Is 0, right? So it's going to be phi tc at omega cross plus phi tp at omega cross, right? This equation. Now, how about phi? How about the phase margin for this one? Phase margin, we defined it. Phase margin for this one I'm talking about, for the open loop transfer function, right? Phase margin was phi TOL plus 180, right? This is what we defined for the phase margin, right? For the open loop transfer function, right? Now, I can replace phi TOL from here, right? I replace the phi TOL here. So phase margin is going to be phi TC at omega cross, right? Omega cross plus phi TP at omega cross. How much is the phi TC at omega cross? Right? Phi TC is boost minus 90, right? Boost minus 90. Is it correct? Correct or not?
Yes.
Yeah, I'm using plus 180. Yes, here I'm. But from here, see, from here, phi TC is boost minus 90, right? Boost minus 90, right? Just let's replace it over there. So phase margin is going to be boost minus 90 plus CTP plus 100, right? Minus 90 is going to cancel the this one, this two. It's going to be 90, and we can say boost is going to be phase margin minus phi TP at omega cross minus 90. Am I correct? Right? I'll tell you why we are calculating all these things. So if I know my omega cross, right, I'm going to select, in my design, I'm going to select, you say, hey, I want to have 50-degree phase margin, 55-degree phase margin. I'll select this one. And if I know how, I'll tell you how we can calculate omega cross. And if I know how much is my omega cross, I know what's my transfer function for my plant, right? I can calculate this one, right? I select this one, I can calculate this one, and this one is clear. I can calculate my boost, how much boost I have. Now, there is another parameter, they call it kfactor. Some people, they call this design kfactor design, you know. K-factor. K-factor is defined like this. We said, we're going to say omega z is going to be omega cross divided by k, and omega p is going to be k omega cross, right? See, omega cross, where's omega cross is here, right? Right? So omega p is a k. I don't know how much is that k. We need to calculate that k. Is this omega cross times that k. Basically, k should be more than 1, right? Because, and here you can see omega z is 1 over k times this one, right? They call it k factor. Now, how much is the phi TC at omega cross? is the maximum value, right? It has the maximum value here. It still is negative, but it's the maximum value. It was minus 90 here, maybe it's minus 10, I don't know, minus 5, minus 15, something like that, right? Now, I want to relate this k factor to the boost value, So basically, this is the boost, right? Am I right? Minus 90, look at here, minus 90 plus something, right? Is the PTC, right? So I'm going to write it here. Also, boost is arctan omega cross over omega z minus arctan omega cross over me, right? And you can see what's the relation here between these guys. If you use this equation, and you know the boost is going to happen at the Pt max, you can come to this equation from these two. From this one, you're going to reach this one. K is going to be tangent of 45 degree plus boost over. If you use those equations, you go calculate the K, you're going to come to this equation. K is this much, K factor. So now, just to review here, I calculated my midpoint. Midpoint means at this point. I calculated the TC gain at this point, right? How much was it? Was it R2 over R1, right? That one won. I find the relation between the boost value, phase margin, and phi TP at omega cross. Hold on. That's the second one, right? And I find out if I know how much boost I have, I can calculate this one, right?
Multiplication over there, omega p.
Oh, this is over here.
Right.
You want to say something? Yeah, that's over here. Yep. So now I'm going to go through the steps of the design. So let's start with design. First, one, we are going to select the omega cross. How much was omega cross? We talked about this one. We said we go the 1/10 of the switching frequency, right? You can go any, the 1/10 is not a rule, fixed, but that's a pretty good, number to start. Because when you do the design, you calculate these numbers, you go back, you simulate your circuit with those values, it may give you a good result or not, and after that you can retune these values. But omega cross was how much? 1/10 of the omega switching, right? So it's going to be 1/10 of 2 pi f², right? Correct or not? So look at here. I know my omega cross, right? I can calculate the phase of the plant at this omega cross because plant is clear. If it is a buck or boost or buck boost, you know the transfer function. You can calculate this one, right? If I select the phase margin, I know how much boost I have, right? I want to have 50-degree phase margin. We said something between 45 to 60, right? So I know how much boost value I have, right? If I know how much boost value I have, I can calculate my K, right? If I know how much K I have, I know this one, I can calculate my omega z. I can calculate my omega p, right? If I have my omega z and omega p, did I erase them? Yeah, that's right. Omega z and omega p, we had them, I don't know how much was it. If one of them was 1 over R1c, I think C1, and the other one was, so those, when I have those values, right? So, if I can use this one somehow to calculate the R1 and R2, I'm done. I calculate R1 and R2 from here. If I have this one with this kind of thing, I can get to the omega z, omega p. I know how much is R1, how much is R2. I can calculate my C1 and I can calculate my C2, right? Let's go through this step. So we select the omega cross, about the 1/10 of the switching frequency or omega switching. 2. We are going to calculate the open loop gain. Gain of open loop at omega cross. Right? So this one is going to be, how much is the gain at omega cross of TOL? How much is the gain at the TOL? At omega cross? Is 0, right? So if this one is 0,
0 dB, right?
this one results in the gain of the TC plus gain of the TM plus gain of TP is 0, right? So basically I can say gain of TC is going to be minus gain of at omega cross. This is all at omega cross. It's going to be gain of TP, I don't have a space here to write it, plus gain of what? TM, right? Oh, it's actually this is negative, sorry. Negative and negative, right? I want to calculate the gain of TC. How much is the gain of TM?
0.
No. What was the TM? Can you remember what was the real TM? 1 over Vp, right? Tm was 1 over Vp, right? How much is the gain of this one? It's going to be 20 log of Tm, right? It's going to be 20 log of this one, right? So basically it's minus 20 log of Vp, right? Or you can say 20 log of 1 over Vp. You can put it this way. If you don't want to put it this way, put it this way. 20 log of Vp, 1 over Vp, right?
If we write the gain in dBs, then it should be equal to 1, right? Because 0 in the time domain is 1.
No, but this is a in logarithmic domain. This is all in logarithmic domain.
So 0 in logarithmic should be 1, right?
Yes. So here is a 0 in logarithmic, right? These are all logarithmic. 0 here is 1 in the time domain. You're right. 1 in the time domain. Right? So this is, I'm talking about 20 logarithmic. I didn't write it that way, but I mean all 20 logarithmic. We do the bold plot is a 20 logarithmic, right? I didn't want to because it was kind of long to write, just as I said. Now, my point is, this one is clear. It doesn't matter what frequency you are because it's a fixed number, right? This is a fixed number, right? That's the maximum of your sawtooth value. Is a 5 volt is 1 over 5. Is 10 volt is 1 over 10. Whatever it is, This one doesn't care really what's the frequency. You know this one. I mean, this one is known, right? How about this one? You have your transfer function for your class, right? Just replace the omega cross on that one and 20 logarithmic of that also. You gain this one, you gain this one, you will find out how much is this, right? So now I calculated this one, right? 3. How much was the GTC at omega cross? Somebody tell me.
Constant.
but you should go with a minus 20 logarithmic, keep in mind, this is not in logarithmic scale, right? I should use a 20 I should take a 20 logarithmic of this one, right? At midpoint, at omega cross. We know gain of TC is how much? 20 logarithmic of this one, right? Right? So look at here. I calculated my GTC here, right? And I know it's going to be this much, right? I know it's going to be this much. So I put this one equal to this one, right? For example, here I calculated is 5, right? And I know this 20 logarithmic of 2R2 over R1 is going to be 20, right? So I can find the ratio for R2 and R1, right? So here it said, in this step, select R1 or R2, you select one value for one of them. For example, you select, because this is one equation, two unknown, right? For example, select R1, I don't know, 1 kilo ohm, R2, you will calculate how much. Select one of these two, R1 or R2, and calculate the other one. Right? So what I did, I calculate the gain of the TC at the omega cross using these two. I know how much is it. Also from the midpoint frequency omega cross, I know the gain should be this much. I'll put this one equal to this one. As I have a one equation, two unknown. I select one of them. I can calculate the other one. So by this step, I know how much is R1 and R2, right? And the goal of this, what all we are doing, we want to select R1, R2, C1, C2, such that they give us a high gain at the low frequency, low gain at the high frequency, and a phase margin of, I don't know, something between 45 to 60 at the omega cross, right? So now we have R1 and R2, right? We need to calculate the C1 and C2. And the next step we are going to go for, let's select a phase margin between 45 to 60, right? So you select a number here again for the phase margin. Now if you have your phase margin, you can go calculate what? But I'm going to just put one more step here, 5. Calculate phi TP at omega cross, right? Right? So you calculate the phi TP, you know how much is the phase margin here, right? So you can calculate the boost value, right? If I know how much is this one, I know how much is this one, I can calculate my boost value, right? Now, I have my boost value. Now I can calculate what? kfactor, right? So I know how much is the K, right? I'm going to go back here. I know how much is the K and omega cross, K and omega cross. So I'm going to go calculate omega P and omega P. right? I can calculate omega p, omega z. Can somebody tell me how much is omega p, omega z? I don't know, one was 1 over, let me see, yes, omega p was 1 over R2C2, right? This one was 1 over R2C1, right? I know how much is omega p, how much is omega c, I know how much is R1, how much is R2, I can calculate C1 and C2, right? So if you want, usually this is for the designer. After you do all this kind of thing, check your design. Now you select all the values, right? You can put all the transfer function together. Go use the body plot, plot everything. See, oh, do you have a 50-degree phase margin? Because there are lots of, not a lot, but there are some, approximation. We say, okay, this one is equal to this one. This one is very big, So check your design. Maybe when you do all this kind of things, and then you plot your TOL, this thing, then you calculate the phase margin, is 35. I have to go and calculate, you know what I'm saying? So you check this thing. We don't have to do it in this course, but this is design process, because we started with some unknown here, we went through this one, we get to this point, we calculated our value, now we want to see how much is right, what we did, how much it was correct. Because we have some approximation in the system when we calculate this one, right? So I have this one, so we have it. Right? Now, let me turn on my laptop. We are going to go through one example. Okay, let's go through one example here. You see, it's not that much complicated. Maybe when we went through all this equation, it was a little bit confusing, but this is all you need to know, guys. This is the compensator, this is the phase for the compensator, and this is the TOL, right? Omega cross is going to happen somewhere here, the phase is 0, and we want to be the phase margin of this one, of the OL, be like 50 degrees somewhere here. And we went through this all calculation. Now let's go through one example. Let's say we have a buck converter. There is a buck converter, V in buck converter. The converter is bought. V in is 10 volt. Switching frequency is 6.5 kilohertz. See, when you design these things, just to let you know, you say, hey, my phase margin is not what it should be. See, for example, one thing you can change, for example, is this one. Don't go with 1 over 10. Go 1 over 15, for example, 1 over 14, something like that. You start to tweak this kind of thing. You run this process to see where you are, right? You can say, okay, hey, I selected 50 degree phase margin, let's take it. I selected 55, let's go with 50 degree, you know what I'm saying? You start to change this number to get a kind of reasonable number, to get this one matched with what you're selecting here. You know what I'm saying? These are like iteration, you go through this iteration to make it work. What you're selecting for your phase margin here, at the end you get some number close to that. You don't have to get exactly the same number, but something close to that. If I selected phase margin over the 55, I did all this design end up 52, still is not bad, 52 is in the range of 45 to 60 I want, you know what I'm saying? You don't have to exactly repeat this one, but the problem is if you selected 55 here, you end up 35 here, that's not good. You have to go change your design. You know what I'm saying? So these are the design process. Now, there's a buck converter. We have a V in 10 volts, switching frequency is 6.5 kilohertz. L value is 1 millihenry. C is 80 microfarad. R value is 5 ohm. This is a load. VP. VP is from the PW, the sawtooth. This is the VP. This is a VP, we're calling it, right? VP is a 5 volt. So we want to design a compensator for this system. We want to design a compensator with some phase margin we're going to select, right? Now, let's just start the steps here from here. 1. Now, we're going to start from here. Omega cross, right? Let's select omega cross. How much is going to be? 1 over 10 2 pi times 6.5 kilohertz, right? So it's going to be 1 over 10 times 2 pi times 6500, right? So this one is going to be Before going a little bit forward, I'm going to just recalculate this one. What was the transfer function for buck converter? Let me put it here.
VO equals VS over 1 minus D.
Yeah. The transfer function, this is what we have for buck converter. I think you had R, V in over S2 LC, RLC plus LS plus R. Maybe I wrote it in a different way, but yeah, for example, divided both, maybe I factored this one, I'm not sure how did I write it, but this is exactly what we calculate. If you go look at your equation, it should be something like this. So that's a transfer function for the plant we have, right? Now let's go through this stuff. Gain of the open loop system should be 0 at omega cross, right? Which means I can calculate gain of my compensator at omega cross. How much is it? Let's start with GTN. Let's say calculate the GTN. 2. How much is the GTN? Right? Because what was the TN? Let me write down the TN here also, just to remind you. What was the TN? Right? That's 1 over VP. So how much is this one? It's going to be minus 20 log of 5, right? So if you calculate this one is going to be 13 point, minus 13.98 decibels. I calculated my GTN. I need to calculate the GTP. I have the TP over there, right? How about GTP? It's going to be this 20 log of, I'm going to do it here, I'm not going to write it down, right? 20 log of this, right? You know how much is a V in, you know how much is R, you know RLC value, and you know the S is the omega cross, right? You replace all those ones, and you calculated 20 log of that. So you are going to end up with 21, 436. Keep it the same here. This one was 9 79. And I'm going to use the same number. VB. I calculated my GTM, I calculated my GTD. How much is my GTC? Can everybody see it here? Can you see it over there? GTC at omega cross is going to be based on this equation minus GTT minus GTM, right? Let's write them down. So this one is 21 minus 21.436 minus, how much is that one? Minus 13.979. So basically it's going to be, how much? Minus 7.457 p. So I calculated the gain of my compensator at the omega cross, right? But I know how much is this gain? Is this value, right? Is this value. Now let's go to the next step. Number 3. I'm going to go here. I know how much is GTC, I'm going to put it here, right? So it's going to be minus 7.457 is going to be equal to 20 log of R2 over R1, right? Correct? So this one is the equation. You will solve it, you're going to get to this one. R2 over R1 is going to be .424, right? Now I'm going to select, what is this part? Yes. Select, this is just for ease. I'm going to calculate, select R1 1000 ohm, 1K, I calculate the other one, right? R1 is a 1K for 1000 ohm. So how much is the R2? 4244. Right? So I calculated my R1 and R2. Yeah. Let me erase this. Let's select a phase margin. Let's select a phase margin of 50, right? So I selected phase margin 50, something between 45 to 60, right? If you want, you can select 65, 65, whatever, right? Now I'm going to come here. If my phase margin is 50, I need to calculate the VTP, right? I can write that one. So let's calculate that. I think, I'm not sure about this, but it looks like there's something here. Phi TP at omega cross. Guys, check this one to make sure it's correct. You know, it looks like there's something wrong here. I'm going to check this calculation, you know, to make sure it's right. Looks like what I have is minus, check this, when I'm saying check this value, 109.29. Right? If I have the CTP, now I can calculate the boost, right? How much is the boost? I'm saying just check this one to make sure this is correct. No, I'm not 100% sure about this one. And you know how to calculate this one, right? You put the omega cross here. You put for S, you put j omega, right? J omega to the power of 2, how much is it? Minus omega 2, right? And this one is going to be j omega, right? And there's a complex number here, and here is kind of real number. Whatever is number here, just reverse it, right? So I mean reverse it, times it by minus 1, whatever it is. So the boost value is going to be based on the equation we calculated. It's going to be phase margin minus, I think, phi TP, right? And minus 90, I think, if I'm correct, it was like this. Alright? Phase margin is 50, phi TP is this much, and we have this one, right? So we are going to get the boost value of 4.05. This is something looks like. I need to check this for myself also. Boost is going to be the 62.29. Now I have the boost value. Huh?
In order to calculate that, if you use that number, it
Doesn't matter.
Yeah, right.
So minus times this minus.
Yeah, phase margin.
Look at here. How much is the difference between, because this is minus times this minus, right? It's very positive number. So it's like 19, right? 19 plus
Look right.
50 is the 59. It's not that, I don't know.
It's gonna be 160 minus 90.
Huh?
Be roughly 70 degrees.
Is it 69 or?
Yep.
Yes, let me see. 109.
Nice.
54 is
right.
19. Yeah, this is 69. You are right.
No, the number you.
Huh? This is 69. This is 69. Most of these numbers are not correct. You should double check these numbers, but you know how to do to double check those numbers. Yeah. Now 6. I'm going to calculate my k factor, right? As I say, double check this number. Very possible these numbers are not correct. I have made mistakes. So 6. K is going to be tan of 45 plus 69.29 over 2. So now, whatever I'm calculating is going to be wrong.
35 plus 45.
Well, I'm going to go with this one. No. The problem is here, I corrected myself once, but it looks like I made a mistake. I don't know which number to go with, And I corrected once myself. Let's go with the number. I'm going to go here, but as I said, double check this one. It's going to be,
Almost
the one
one.
number I have here is going to be
0.19.
Can somebody else let's calculate this one? How much is this one?
5.47.
How much?
5.47.
5.47. So this is the number I crossed. There was 5.47 before. So 5.47. Now we have the k value, right? 7 is going to be. I have k and omega cross. I can calculate omega p and omega c. How much is omega p? And we have this somewhere. Omega p, I think, was k omega cross, right? And omega z was omega cross over k, right? See, guys, here, the bigger this number, the better with the assumption we have, right? That will be the assumption we have. Now, omega p is going to be how much? 5.47 times, how much was omega cross? 4084, right? Omega z is going to be 4084 divided by 5.47, right? So omega z, omega p, they're going to be, if I'm correct, omega z is going to be 730.9, and omega p is going to be, how much is omega p?
22 hours.
Yeah, it's going to be 21. Right? So we have omega p and omega c. See, the assumption we had, this one is almost more than 10 times of this one, right? It's good with the assumption we had. And how about the mid frequency? Mid frequency is almost 5 times of this and 1/5 of this. Again, not bad. So now we'll go to the last step. You can use here. How much is the C2? C2 is 1 over R2 omega P, and C1 is 1 over R2 omega Z, right? Omega Z. So basically, you can calculate C1 and C2. We're going to come up with C2 is going to be 107.8 nanofarad, and C1 is going to be looks like 3.228 microfarad. Again, see, this is not bad. This is 0.1 microfarad, right? This is 3 microfarad. This is almost 30 times of this one, right? This is when we had assumption you said C1 is very, very bigger than the C. Now, we are done. We are done. I'm going to stop it now. I'll post a few. I was going to go through this example here. I'm not sure. Can you see the stay a little bit longer? Now I can go through this one and wrap up this one, and I'll post this one. This one should be very quick. These are more examples. Just to look at. Just sit down. I think we can finish it in 10 minutes, something like that. If you don't ask questions, in 10 minutes. If you ask questions, then more.
Just really quick, what were we checking against for step 9? What were we checking?
Oh, you selected all these values. Go back, calculate your phase margin. How much is your phase margin? I don't know how much it's going to be. See, we went through this process, right? But you need to go calculate. Let's guys finish this one. It's better so next Thursday I can start a new topic. Thursday I can start a new topic. And I post this thing is good for your homework, so you're going to go over it. We'll be very quick. A few examples. With the body block. We'll be very quick. I'm saying you're going to be very, very quick. And your stopper is basically 30 minutes long, right? This is just like a more example. What we're going to go over, if you can understand, is just like a more example.
Professor, when you're using TM in your notes, what does TM stand for?
That's a modulation, the modulator, the PWM generator.
Okay.
Thursday, when I start the resonant converter, just I want to make sure. Yeah, here is more examples, just with the body plot, we, for the 8 volt, I don't know, we had a transfer function, it looks like again is the buck converter. Here you can see. There's some parameter here, switching frequency was 75 kilohertz. I don't know, V out 12 volt, V in this much, L this much. All these values you have in here, right? Now, here we plot these are the TP, these are the plant, transfer function. See here, this is a plant transfer function, right? So, omega cross, I think is this one you calculated here, how much is it? So, let's move to the next page. So, we had a buck converter. Here it shows the body plot for the buck converter, transfer function. Now let's go to the next page. Now, it shows a simple transfer function for the compensator. 10 to the power of 3 over s. Can you see it on the top here? Not the one we talked about it here. Select something, he wants to select this one. 1000 over s.
Can you zoom in a little bit on it?
Yeah. Can you see it now?
Yeah.
I'm saying it's not following what we are saying. You select the T compensator, this much. Tm is the modulator, right? 1 over Vp. And TOL is the equation you put over there. Now it's plotting this one. TOL, look at here, right? Now, see, if we select the compensator like the one we put it over there, 10,000 over S, this is the TOL. Now, you can go calculate your phase margin and everything you want, right? Let's see how much is it. Your gain is not bad. In the low frequency is 60, right? 60 dB. If you want to calculate the phase margin, look at here, 0, right? This is a 0. You come down here, how much you have here? This is the minus 120 degree. This is how much phase margin you are going to have? 60. So even with that compensator, looks like it's working perfect. Because if you look at here, at high frequency, your gain is going to be very, very low, right? This one is very deeply going down, right? So this is one compensator. He wants to select the compensator 1000 over S, and you can see the result here. This is a very simple design here. You know what I'm saying? But this one is not going to work all the time, for this DC to DC converters. But this is just one example. I'll send you this. I'll post this example. You can see it. So the phase margin and the gain you can see is pretty good for this one. Let's go to another one. Now we change the compensator here. See that one? Kind of similar to what we have, right? Kind of similar, MVP and the same thing. So look at this one. This is the TOL. Remember, I erased it here. How it's going to be? It's going to come like this, and it was like this, right? Here is crossing 0, right? So come down here. The phase margin again is a minus 120, right? But this one again is giving you 60 degree phase margin again. So this is another new design here. And let's look at another one. I think the next one is the example we went through. Yeah, this is the example we went through. Again, this is the plan. This is the VTP, right? So we selected those values. We calculate all this kind of thing, phase margin more than whatever, blah, blah, blah. Look at here. This is the TC, remember? This is the TC for this system. And here is the mid-frequency gain. This is the boost, right? I'm going to post all this thing on the website. You can go look at it, So the final design for the compensator, this is a TOL. You get here? Very similar to what we had in the previous example. Right? The 0 is here. And again, you can go calculate the phase margin. ID phase margin at the end of 52 degrees. You calculate the 50 degree. Yeah, that's it. Just this is a kind of example I want to show you. We went through that design. For example, here, this is what we designed. You know, I told you go check your design. We selected how much phase margin? 50 degree, right? So this one is not 52. It will be better than what we selected. This is a design process. You know, you don't do it handy, calculate all. You just do the MATLAB body block, boom, 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 done. It calculates everything for you. You don't have to select type 2 compensator for your system. You can select whatever you want, right? But as far as it does work, you can select whether you can select a PI controller, you can select a PID controller, you can select a type 2 compensator, you can select type 3 compensator. These things usually the problem will show up in the real circuit. These are all math calculation, those kind. Usually the results are good. For example, the difference between the first compensator and the second one I showed here. When you go to the real system, you see the second one works much better. Noise-wise, control-wise, you see the second one works much better. You know what I'm saying? Because this is what the type 2 is widely used in the power supply design. Most of people they use that one. I have seen many people they use the type 2, and they are pretty happy with how it does work. So I'll post this slide. This is like more examples. Don't get confused. This is just like more examples. You see how this thing looks like. Okay? So now you are done, complete for the homework number 3. You can solve that one. Thursday we'll start the resonant converter. That's the last chapter we're going to do. And hopefully in the last class I'll get like 1 hour to talk about the different application of power electronics. That one is just general talk. So I'll talk about HVDC, I'll talk about electric car, I'll talk about DC motor control, everything. You see the simple block diagram, then you know the inverter, you know the DC converter, you should be able to do all of those. And you